Okay, I think we're ready to start. So our final talk this morning will be given by Serban Belinschi, and his title is Upgrading Subordination Properties in Free Probability.
Thank you very much. So first, my thanks to the organizers for the kind invitation and the beautiful program, and thank you all for being here. So this will be a hardcore free probability talk based on joint work about a year old with Harry Berkovich, which was in its turn based on part of an older work with Jerry Gu and Paul Skufranis and Harry and I. So does it? I would hope. Okay. Yeah, I hope it works. I mean, yeah, I think it works. Okay. So, but you can hear me? I mean, yeah. Okay. Okay. So I'll start with history and ideas of behind the subordination, the analytic subordination property, and then go to showing you the proof, which is surprisingly straightforward. So what is the context? The context is Voiculescu's free additive convolution. So we start with tracial W star non-commutative probability space. That is, A will be a von Neumann algebra, and tau will be a normal faithful tracial state on A. And in there, we pick two self-adjoint random variables, x1 and x2. So that at this moment means also bounded. And we assume that they are free with respect to the trace tau. I will not define freeness in this talk, but at one point you will see it as a consequence. The definition will appear as a consequence of a theorem. So let's define two transforms here associated to these x's here. So we take the resolvent of xj and we apply tau, the trace. What we get is the so-called Cauchy transform, which of course depends only on the distribution of xj with respect to this tau. So this mu xj is a Borel probability measure, compactly supported, so supported on the spectrum of xj. And it's given by the composition of tau with the spectral measure of xj. Then Voiculescu defined this R transform. So what you do, you notice that this G is injective on a neighborhood of infinity. It maps it onto a neighborhood of 0, and you perform the compositional inverse of that G defined on the neighborhood of 0 as a meromorphic function. You throw out 1 over the variable. That gives you an analytic function on a neighborhood of 0. So this R is an analytic function defined on the neighborhood of 0. Now, the spectacular thing that Voiculescu showed is that this R linearizes freeness. So if x1 and x2 are free with respect to tau, then the R associated to x1 plus x2 is the R associated to x1 plus the R associated to x2, this on the joint domain of the three functions, which is a neighborhood of 0. Now, freeness, that means that the distribution of x1 plus x2 only depends on the distribution of x1 and the distribution of x2, and it depends via the operation that Voiculescu called free additive convolution. Now, let's look at this relation of Voiculescu and rewrite it in terms of the definition of R via the J function. So what you have is then G x1 plus x2 inverse if you add here 1 over the variable, then on the right-hand side, you get gx1 inverse plus gx2 inverse. That's just rewriting Voiculescu's R transform property. Okay, and what we do is replace the w variable from here with gx1 plus x2 of z. And then we get z plus 1 over gx1 plus x2 equals gx1 inverse of gx1 plus x2 plus the same with x2. This holds for z large enough. The insight of Voiculescu in his free entropy 1 paper, so the analog of entropy and Pfeffer's information in free probability theory from '93, was that these compositions here can be extended to the whole upper half plane. Now, the inverse here doesn't extend to everything, but when you compose it with gx1 plus x2, it does extend. So from now on, we define these compositions, we denote them to be omega j, the one associated to xj. Now, Voiculescu proved this result for specific purposes. So he took an ad hoc proof for ad hoc purposes. So he allowed for this extra assumption that gx1 and gx2 have no critical values in common, which is a very small restriction. And with that hypothesis, what he did was essentially applying the monodromy theorem. 2 steps, as I mentioned here. First, you show the necessary inclusion in order to be able to define such a composition, and then showed that the analytic continuation along any path can be going from a neighborhood of infinity and arriving anywhere in the complex plane, in the complex upper half plane, can be performed. So, as I said, Voiculescu used this mainly to prove monotonicity results for LP norms of densities of the measures involved. So, you know, the measures μx1, μx2, and μx1 free convolution μx2, and the free entropies of the variables x1, x2, and x1 plus x2. So, one notices immediately that this genericity assumption, no critical values in common, can easily be discarded by a straightforward continuity argument. So that was really not a restriction. Okay, now things stayed there for about 5 years until Philippe Bihan wrote his famous paper or processes with free increments. So remember, we've denoted omega j, this composition of gxj inverse with gx1 plus x2. What Voiculescu showed is that this omega j extends as a self-map, analytic self-map of the upper half plane. Well, move this gxj inverse to the left, and you see why this is called the analytic subordination property, because what you see here is that gx1 plus x2 is subordinated in the sense of Littlewood to each gxj via this omega j. Well, if you write this in terms of the traces of the resolvents, it looks like this. So, in order to explain Philippe Bihan's result, let me introduce here a few extra notions and notations. So here, I know people usually denote C of xj in brackets like this, the space of non-commutative polynomials. Well, I'm stubborn and denote by this the von Neumann algebra generated by xj inside A. So then there exists a unique trace preserving conditional expectation from A onto this von Neumann subalgebra. That is a linear map that's C of xj by module map, and that preserves the trace. And remarkable and useful later in the talk is that one finds this conditional expectation in a way very simple as a projection, as an orthogonal projection. You complete A to a Hilbert space induced by this by the scalar product induced by this trace tau, and you take the orthogonal projection onto the subspace generated by C of xj. So what is this? Well, you just take the scalar product to be U scalar product V to be tau of V star U. That, of course, will be well defined on all of A. You cannot hope, of course, that A is complete with respect to it, so you have to complete it. L2 of A tau is that completion. Well, what Philippe Bian showed in his 98 paper is that if instead of putting here the trace onto the resolvent of x1 plus x2, you just put the expectation onto the von Neumann algebra generated by xj on that resolvent. Well, what you get is the resolvent of xj, but of course evaluated in the subordination function found by Voiculescu. Now, this, as you can see, is a very strong, very impressive result. I was curious once I asked Philippe how did he get the idea to look at this. He told me, well, it's obvious if you're looking at semicirculars, and I just tried for the rest, and he got it. So now the idea of the proof was, so by the way, I should say here, xj don't need to be bounded. So they can be unbounded random variables affiliated to this A. And the result still holds. So what Bian did to prove this result was to use essentially the combinatorics of moments and free cumulants. He assumed initially that both xj's are bounded, so they have all moments and all cumulants. He used the way that E, the expectation applied to a monomial in x1 and x2 behaves. With that, he proved this relation around infinity, so for absolute value of z large, and he concluded by analytic continuation and then approximation. If these xj's were not bounded, then he approximated them with bounded random variables. So now in the 2000s, we can remember here at the fields, some of us, Voiculescu referred to this result here, this specific result, as what motivated him to explore this in a much more general context in his 2000 paper, the coalgebra of the free difference quotient and free probability. Let me explain what the context is and what Voiculescu's result and ideas, a few ideas behind the proof are. So here now, in addition of the A tau, where tau is a trace, normal faithful tracial state on the von Neumann algebra A, we have a von Neumann subalgebra B of A, and we take the unique trace preserving conditional expectation EB onto this B. Now we assume that x1 and x2 are free, but this time over B with respect to this expectation EB. So it's arithmetic relations again of expectations of non-commutative polynomials in x1 and x2 with coefficients in B. In this case, the upper half plane, for our purposes, needs to be replaced by the upper half plane over B, which is formed by those elements little b, which have strictly positive imaginary parts. So you take b minus b star divided by 2i. You require that this is a positive operator, and it's invertible. This is what strictly greater than 0 means. The Cauchy transform now becomes the expectation with onto B of the B resolvent of xj. So you take any little b in the upper half plane of the algebra B, you subtract from it xj. If it's invertible, you invert it, and then you apply EB to that inverse. So again, this has been shown by Voiculescu to be invertible whenever B is in the upper half plane and X is self-adjoint. Voiculescu's B-valued R transform looks precisely like the usual scalar valued one. So you can invert Gxj, and then Rxj is this inverse of Gxj in W minus the multiplicative inverse of W. This extends to a neighborhood of 0 in this Banach space. On Neumann algebra, it's a Banach space. And we have this same relation on this common neighborhood of 0. Well, what Voiculescu shows is that there are maps omega 1, omega 2, such that if we take the expectation onto the algebra generated by B and xj of the B resolvent of x1 plus x2, we get again a B resolvent of xj, but evaluated in this subordination function omega j. Actually, he shows much more than that, because the triple von Neumann algebra, von Neumann subalgebra, conditional expectation has an operator space structure. So you can amplify all this stuff to n by n matrices over A, n by n matrices over B, and the expectation applied entry-wise. Now, the full result, the complete result of Voiculescu in this case, is that if we take a tracial non-commutative probability space, we take again a von Neumann subalgebra B, we take the unique trace-preserving conditional expectation from A to B, and we assume that self-adjoint x1 and x2 are free with respect to this expectation EB. Then there exists not only one omega j, well, one pair of omega 1, omega 2, but a whole tower of pairs omega 1, omega 2 indexed by the matrix size n. So omega j at the nth level sends the upper half plane of n by n matrices over B into itself. It respects block structure in this upper half planes. So if you have a block matrix with blocks on the diagonal, 0 otherwise, then the omegas get applied individually on blocks. And it respects conjugation with unitaries. So whether you take a scalar unitary, n by n scalar unitary, and conjugate your variable B inside or outside the function omega, you get the same thing. And finally, if we amplify again everything here to an arbitrary n by n matrix by putting the x1 plus x2 on the diagonal, n copies, and the xj again also on the diagonal, then the expectation amplified also to n by n matrices onto this B of xj, so the von Neumann algebra generated by B and by the variable xj, then we get again this resolvent here evaluated in the subordination function, and this for all n's. So this is a much stronger result. And it brings free probability and non-commutative functions, well, intimately together. Now, I will go shortly through the idea of the proof. What Voiculescu noticed was that certain derivatives, the free difference quotients that you've seen in previous talks, interact well with the conditional expectations onto this variable. So if we look here at oops, sorry. If we look here, this time I denote by b of square brackets x1, x2, the non-commutative polynomials in x1 and x2 with coefficients in b. So sums of monomials bi1, xi1, bi2, xi2, bin, xin, and so on. So only such sums here. Under certain conditions, one can define this free difference quotient that sends this algebra into the tensor product of the algebra with itself in such a way that the derivative in the direction j of xk is 0 if k and j are different, and is 1 tensor 1 if j and k are equal. It kills all the scalars, so algebra scalars, so it kills all the elements from B. It's linear, and it obeys the product rule written like this here. Well, if it can be defined, then these properties define it uniquely. So now, very roughly, it is a long paper. What Voiculescu shows is that if you start with diffuse x1, x2, then the free difference quotient is well defined, extends to resolvents, so extends beyond such polynomials to resolvents, and that thanks to the way conditional expectations and the derivative, this free difference quotient, interact, and that is the key point of the proof. If you differentiate here, if you take dj of the expectation onto b of xj, I should say of the inverse of the expectation onto b of xj of the resolvent of x1 plus x2, what you get is minus 1 tensor 1, which is exactly what you get if you apply dj partial j to the variable xj. So this shows that if you take this expectation of the resolvent and you take its inverse, this is multiplicative inverse, inverse in the algebra b, well, b of xj, and you add this xj, well, this guy over here has to be in b. It cannot be in b of xi, the other, because, well, it's projected here, and it cannot interact basically with this xj because, well, it's killed by the difference quotient. So it has to be in b. Now, of course, the fact that the correspondence little b goes to this expression here is analytic on the upper half plane, thanks to the previous results, follows easily. And also it follows easily that it respects, oops, sorry, my bad, here, and that it respects all those properties. It behaves well with respect to all these properties. So that's the idea, very roughly, behind Voiculescu's proof. Now, if you forget about conditional expectations onto C of xj or B of xj, if you go back to Voiculescu's initial result, but you apply it not only to the scalar context, but also to the operator context. So when your functions take value in B, in the von Neumann subalgebra B, then you notice that the relations satisfied by both scalar and operator valued, as I said, subordination functions, which, okay, are this. So first, g of x1 plus x2 is the same as gxj of omega j. That's the subordination part. And thanks to the R transform property, this stuff is also equal to omega 1 of b plus omega 2 of b minus the variable b, well, everything inverse, because here you have the g's, not 1 over g, not g inverse. So this, with some patience in writing down arithmetics of functions, is seen to be equivalent to two fixed point relations. So omega 1 of b is the fixed point of the function parameterized by b, so b is fixed here, which sends a variable w to b plus hx2 of b plus hx1 of w, where this hx is the Boolean cumulant function. So it's the multiplicative inverse of gxj minus the variable. So this way you write the omegas as fixed points of self-maps of half-planes, which have automatically very good properties, thanks to the fact that, in general, analytic functions are contractions with respect to hyperbolic metrics. So the existence of subordination functions and relations can be proved again this way with purely analytic function theory methods in the scalar case done by Harry and myself in a paper published in 2007, and in the general case B in a paper that was on arXiv, I think, in 2013, but it took a long time to appear in print, so it's from 2017. The latter case, so general B here, was a new result. It had not been written that way before anywhere in the literature. So it did not assume that we are in a tracial non-commutative probability space, B-valued non-commutative probability space. So you can have an expectation without a trace. And it did not require that B is a von Neumann algebra. It could just be a C-star algebra. So in a way, it was stronger than Voiculescu's result, but it was also much weaker than that whenever you consider a tracial probability space. It could not recover the fact that the expectation onto B of xj of the resolvent of the B resolvent of x1 plus x2 is itself a B resolvent of xj. Okay, now before I go forward with this, let me just mention very briefly 3 properties of the subordination functions as introduced until now. So first, it's nice to see the reason I asked Philippe Bian why did he even think about that possibility is this item 1, the possibility that you can project basically resolvent of x1 plus x2 and get the resolvent of x1. The reason is this item 1 here. So let's consider a unitarily invariant model. So we take Cn and Dn to be n by n self-adjoint complex matrices. We can take them diagonal. We assume that they are uniformly bounded, so their eigenvalues as n tends to infinity don't go to infinity, they stay in a bounded set. And we assume that their distributions with respect to the normalized trace on n by n matrices converge weakly to mu1 and mu2, which are compactly supported Borel probability measures on R. Now, pick an integer n, arbitrary. It's convenient, but not necessary, to assume that the first R entries of Cn converge. So it's really not necessary, but it's convenient. Let un be a hard distributed n by n unitary for each n. And take Pn to be the projection from Cn to Cr, so on the first R coordinates. Well, now we take the resolvent Zin minus Cn minus un dn un star, and then we apply this expectation with respect to un. Well, this is the probabilistic expectation. It's just taking the integral entry-wise of the random variable here with respect to the Haar measure on the unitary group. Okay, now this thing still stays with strictly negative imaginary part. You can cut it to the R by R upper left corner. This still stays with strictly negative imaginary part, so you can take its inverse, and then you can add Cn, but also truncate it this way. The thing is, when you do this and let n tend to infinity, this converges to a scalar. And that scalar is omega 1 of z, the subordination function corresponding to mu1 times the identity r. So this looks very much like Bian's subordination result. It's not identical, it's a bit weaker, but it looks very much that way. This is just an auxiliary result from a paper with Hari, Mireille, and Maxime Février, outliers in the spectrum of largely formed unitarily invariant models. Now, you can see that there is an intimate connection between this conditional expectation property, so projecting the resolvent, and the random matrix theory through these unitarily invariant models. Now, I want to mention two other little things about these omegas. One that, well, you can rewrite these fixed point relations here a bit different. Namely, you can obtain these omegas as restrictions of an injective analytic function from C plus squared to C plus squared. So define H from C plus squared to C plus, this doesn't preserve the upper half plane, to be, when evaluated in variables W1, W2, to be W1 minus Hx2 of W2 and W2 minus Hx1 of W1. Then this H can be shown to have a right inverse, bold-faced omega, which preserves C plus squared, and such that when you restrict it to the diagonal, so to variables zz, gives you the subordination function. And by the way, this works also in the B-valued case. So it really doesn't matter that that you have here C. This is consequences, a corollary, a corollary in a recent paper with Hari and Xingwei Ho. And another fact is that in this case, we need to restrict ourselves to the case of the complex upper half plane. Omega 1 and omega 2 actually extend continuously to R if you accept also infinite values. And this is true whenever x1 and x2 is not, neither x1 nor x2 is a multiple of the identity. I had shown that in 2014 in full generality. And recently in this same paper with Hari and Xingwei, we have a much simpler proof. So these are some properties. Remember where we had left before going to the aside? Well, we are saying that finding these omegas in the B-valued case, so for general B, in the spirit of Voiculescu's 93 paper, was both a stronger and a weaker result. So it was stronger because it was not requiring the existence of a trace, and it was allowing B to be just a C-star algebra. But it was weaker because we could not project onto the phenomenal algebra or C-star algebra generated by B and Xj the resolvent, the B resolvent of x1 plus x2, and get a B resolvent of xj. But that's wrong. That shouldn't be like that. Morally, at least, should not be like this. And this is for the following reason. And this is the place where, well, we introduce a definition of freeness. Assume that A, B are C-star algebras, unital, of course, and B contains the unit of A, and EB is a continuous conditional expectation from A onto B, and that's all what you require. Assume now that x1 and x2 are self-adjoints in A, and satisfy the property that for any natural number n, for any self-adjoint scalar matrices, alpha 1 and alpha 2, which are size n, assume that there exist these two subordination functions, omega 1, omega 2. That is, there are subordination there are functions omega 1, omega 2 which map the upper half plane of Mn of B into itself, and such that G of the variable x1 tensor alpha 1 evaluated in omega 1 equals G of the variable x2 tensor alpha 2 evaluated in omega 2 equals the G of x1 tensor alpha 1 plus x2 tensor alpha 2 and equals omega 1 plus omega 2 minus the variable inverse. Well, if you have this for all alphas and all n's, then x1 and x2 are actually free with respect to this expectation B. So you can get the freeness. So why can't you get the projection? So somehow Voiculescu's result should have been recoverable from our result with Tobias and Roland. And that's where the new result with Harry comes in. Let me just start by stating it. It will look in the beginning a bit strange. I mean, how does this connect with what has been until now? So we prove it in a very general context. We assume that we have a Banach algebraic non-commutative probability space. So A is a Banach algebra with unit. B is a Banach subalgebra containing the unit of A. EB is a continuous conditional expectation from A to B. And we assume that we have three variables in A. You can't say self-adjoint because there is no adjoint operation here. And we assume that x1 and y are free from x2 with respect to this expectation onto B. Well, what we show with Harry is that if you take the resolvent of x1 plus x2 in an element B from the algebra of scalars B, and we multiply it to the left or to the right with y, and then we apply the expectation B, we get the same thing as if we would get a certain function omega 1 of B here and subtract x1 from it, take the inverse, and multiply it either to the left or to the right with this same y, and then take the expectation EB. This, of course, holds for every invertible little b in big B, such that the norm of B inverse is sufficiently small. We don't have a canonical domain, so we can't really say more than that. Well, the question is, why does this generalize Voiculescu's result? Well, consider what this EB was, EB of x1 was. So the expectation onto the von Neumann algebra generated by B and x1. Well, this was the restriction to the von Neumann algebra A of the orthogonal projection from L2 of A with respect to the scalar product induced by tau onto the Hilbert subspace generated by B of x1 in there. Well, what is a projection? How do you write a projection? Well, you write it by throwing away the perpendicular part and keeping the parallel part. So if you take a psi star, let's say in B1 of x directly instead of L2, and you multiply it with an eta, let's say from A, you apply tau, well, you get the same thing as if you apply tau, here, a psi star, so multiplied with the part of the vector eta, which is in here, in this subspace. So how would you write this for the resolvent? Well, you take an arbitrary y in B of x1, you would multiply to the left and to the right. So here, didn't have space to write this also on the right, but you would multiply it here to the left and to the right. Well, this is a trace in this case, so okay, you don't need to write it, strictly speaking. But so again, y times B minus x1 minus x2 inverse, you take tau, and if you show that this is equal to tau of y times omega 1 of B minus x1 inverse, for all such y's, then you obtained Voiculescu's result for this first level. So this is why, out of this, we can get Voiculescu's result. Now, as I briefly mentioned, in most cases of a Banach algebraic probability space, you don't have a canonical domain. Now, that means that these relations are defined on just some small open sets, a priori small. They might be very big. But these objects are not so unfamiliar if instead of taking gxj of b, you take gxj of b inverse, then this new function actually extends to a neighborhood of 0 of, well, of size, ball of size norm of xj basically inverse. So then you can write the same formula in terms of this mxj, which is gxj of the inverse of the variable, as little oj of b being omega j of b inverse everything inverse. So this oj also extends to a neighborhood of 0. So this, in this sense, this omega j is defined on a neighborhood of infinity. Now, since we are here in an arbitrary Banach algebra, I think this is the best that one could ever hope to state. Now, another thing to keep in mind is that not all C-star non-commutative probability spaces are tracial. And what our result also allows us to conclude is that if you take a state on B, an arbitrary state, and you take some bigger subalgebra Y that includes B of x1 and is still free from x2 with respect to this expectation, then the projection from L2 of A with respect to the composition of phi with EB onto L2 of Y with respect to this composition of phi with EB sends the resolvent of x1 plus x2 evaluated in B onto the resolvent of x1 evaluated in omega 1 of B. And this is the omega 1 that comes from the work with Tobias and Roland, the one obtained as fixed point. So, okay, let me go a bit through the proof. Yes? Yeah. I don't know if that works. I would really have to think about it. I'm sorry, I cannot answer this on the spot. But thanks for the question. That's actually good to think about. Thanks. So let's look shortly at the proof. Actually, one could stop with a proof here. If I tell you that you should start just by building a boldface x1, which contains our initial variable x1 and y on the first column of a 2x2 matrix, and 0 on the second column, and the boldface x2 that contains our initial x2 in the upper left corner, 0 everywhere else, and that you should view them in the algebra A2 of lower diagonal matrices with entries from A, if you know that that thanks to the Nikash-Levtenko-Speicher result from 98, they are still free in A2, B2, so the lower triangular matrices with entries from A and B. With respect to this expectation applied entry-wise, then you will be able to complete the proof on your own. But since we are here, let me tell you still how the proof goes. Now, this Banach probability space can be endowed just with the operator norm from its action on a direct sum with itself. You can choose some norm, let's say the L1 norm, but whichever you'd want is still good. And take x1 and x2 boldface. As I said, they are free with respect to this entry-wise applied conditional expectation. Well, take a B, B11, B22, B21, and 0. Subtract it from your x1, invert this, and see what you get. You get this formula. In the upper left corner, you have B11 minus x1 inverse. In the lower right corner, you just have a placeholder, B22 inverse. And here, you have something that contains, you know, the famous y and this B11 minus x1. So you already see where this goes. So if you take the G corresponding to boldface x1 first entry, you get Gx1 in B11. And if you take the same G in the 2-1 entry, well, you get this B22 inverse and exactly this thing over here, expectation of B onto expectation onto B of y times B11 minus x1 inverse. And then, okay, you have this guy here, which is known. Now, formulas, of course, for B minus x2 boldface and B minus x1 minus x2 boldface, both inverses, follow the same way. You just compute them by hand. Well, we are still in a Banach probability space. Voiculescu's R transform still holds. So we still have these relations here for some omegas which are defined on sets as mentioned on the previous slide here. So if you restrict your B properly, and there is a tiny little bit of work, you know, 10 minutes, 10 extra minutes, to show that you can find such a common domain of boldface B's, then thanks to Voiculescu's R transform relation written in the subordination form, you end up with first the fact that these omega j's are also lower diagonal, and that you can write this equality here. Where is it? This equality here. You can take various parts of it and write it with these specific formulas here. You take a convenient type of B. So boldface B, you take it just diagonal, your variable B here, small b, and some parameter T here. Now you try to identify, thanks to this relation here, this is omega 1 plus omega 2 minus the variable equals the inverse of G x1 plus x2. This is the relation that you have here. You study this relation carefully. You look at its 1, 1, 2, 2, and 2, 1 entries, and you see that at the very end, you get this expectation onto B of y times B times the B resolvent of x1 plus x2 equal to the expectation of y times the B resolvent of x1, but evaluated in omega 1 of B. Now, of course, to get the result for the right side, you take upper, not lower, triangular matrices. Now, I was mentioning that this idea comes from a previous idea. It was in a paper on bi-free convolution that Harry and I wrote with Jerry Gu and Paul Skufranis, in which a fairly similar trick was used, but with 3x3 matrices and keeping self-adjoint nets, in order to reprove Philippe Bian's result and to show that usually you cannot expect this kind of result to ever hold in bi-free probability. So this holds only in very, very trivial cases. Basically, when you just have freeness, independence, and that's it. So it does not work in by-free probability. So this is what I wanted to say to you. And now at the very end, a small remark. There is a very recent preprint, remarkably on November 7th, from Franz Lehner and Kamil Spojankowski, which proves this conditional expectation property by making use of, well, essentially description of freeness by Boolean cumulants. My very strong feeling is that out of their paper, one can obtain this result of Hari and I, because I don't think that they need anything more than just algebraic properties there. So then it should work not only in their context with C-star algebras, but also for Banach algebraic probability spaces. If this statement is wrong, please don't blame Kamil, blame me. Kamil didn't claim that this would be proven. It is my feeling that it's there. So yeah, that's it. Thank you.